Okay, it's start of a new unit. And let's see what we're going to study. Probability. We're going to be taking a look at probability. So for this first lesson, we'll be taking a look at sample spaces and theoretical probabilities. So what on earth is a sample space? Well, whenever we do something, there are a bunch of different results that can happen. And of course, these results, we can call them outcomes. So for example, if I flip a coin, if it comes up heads, that's an outcome. If it comes up tails, that's an outcome. If we roll a six-sided die, we can get a 1, 2, 3, 4, 5, or 6. Right? So if I wanted it to be an odd number, that would be in an event. Say, hey, I want to roll a die, and there are a bunch of different outcomes that could happen. I'm hoping for an outcome of an odd number. That would be an event. And then if I look at everything that's possible, that's the sample space. So if I roll one six-sided die, the sample space is 1, 2, 3, 4, 5, 6. Or if I was going to toss a coin, the sample space would be heads or tails. This is just one of those little things that drives me up the wall. You can't roll one dice. All right, you can roll 2 dice, you can roll 3 dice, you can roll 4 dice. But if you roll 1, it's a die. Okay, let's see if we can figure out our sample space. Ooh, I'm going to do 2 things. I'm going to flip a coin and roll a six-sided die. So what could possibly happen? Well, quite often in probability, we use a tree diagram. Of course, if I flip the coin, it could be heads or it could be tails. And then, if I roll the die, well, if the coin flip was heads, it could be followed by a 1, 2, 3, 4, 5, or 6. If the coin flip was tails, it could be followed by 1, 2, 3, 4, 5, or 6. So there's actually 12 different outcomes that could happen in our sample space. We can have heads followed by a 1, heads followed by a 2, heads followed by a 3, heads with a 4, heads with a 5, heads 6. Oh my goodness, we could have tails followed by a 1, tails with a 2, tails with a 3, tails 4, tails 5, tails 6. Okay, theoretical probabilities. Probability always has to be a number between 0 and 1. I prefer to use fractions In a moment, I'll show you why that fractions is sometimes a little more clean to use than decimals or percents. One means it's going to happen. 0 means it will not happen. It's impossible. All right, so theoretical probability. Let's pretend I toss a coin and I really want the outcome to be tails. Well, the probability of tails would be 1 over 2. Because the only thing I'd be happy with would be tails. There's two of the things that could happen, heads or tails. And then for shorthand, we see the P, we know it's probability. And then we can put the event inside parentheses. Sometimes we'll label event with a letter such as A or B or C. Or sometimes we'll actually just put the event inside the parentheses. So let's go back and let's look at that coin and 6-sided die. And if the desired outcome is a 6, or in other words, the event of the 6, probability that there's a 6, well, the sample space has 12 things in it, so the bottom of the fraction's got to be a 12. It looks like 2 of the 12 outcomes had a 6. So the probability that I rolled a 6, 2 out of 12. And of course, we're going to reduce the fraction. So the probability is 1 out of 6. Ooh, what's the probability that I tossed a tail? Okay, so the probability that I had a tail, again, the denominator's got to be 12 because the sample space has a size of 12. There are 12 different possible outcomes. It looks like 6 of those 12 outcomes included the coin coming up as tails. So the probability that I had a tail, 6 out of 12. Of course, I'm going to reduce the fraction. I get 1/2. Ooh. Head or odd number. Well, again, you know the denominator is going to be 12. How many times was it either a head or an odd number? Well, this is where it gets a little bit tricky because there were 6 times when there was a head. There's also 6 times where it's an odd number. But I can't count some of these events twice, right? If it's a heads with a 1, I only want to count that once, not twice. Or heads with a 3, only count that thing once. Heads with a 5, count that just once. So at first glance, I might say, hey, 6 of them have heads. Hey, 6 of them have an odd number. No, we're not going to do 6 plus 6 and get 12. There's actually 9 outcomes that are associated with this event. So the probability of this event, 9 out of 12. 9 times the combination either includes heads or an odd number. Notice with math, when we use the word or, we can have both occur. So like if you get a heads and a 5, Yeah, you got both of them. That's okay. Of course, I'll reduce the fraction. Okay. Why do I prefer fractions? Well, 1/2 would be easy enough to convert to a decimal, or even a percent, right? Everybody knows that 1/2 is 0.5. Everyone knows that 1/2 is 50%. 3/4, it's still pretty straightforward. 3/4 is 0.75, also known as 75%. But take a look at this 1/6. If you want to convert it to a decimal, it goes on forever. Which means if you want to convert it to a percent, it goes on forever. Which of course means you want to round it off at some point. And when we round off, we no longer have exact values, we have approximate. Okay, how about a tail and a 6? You know the denominator is 12. There's only one way I can get a tail and a 6. So 1/12. Probability that I rolled a 7? Well, you know the denominators are 12. 7. I don't see a 7. Probability 0, right? It cannot happen. It won't happen. Probability of 0 means it will not happen. Oh, 4 coins. Going to toss them all up in the air. I want exactly 2 of them to be heads. What's your guess on the probability? Throw 4 coins. Now again, with math probability, we assume it's going to be heads or tails. We're not going to have the coin land on its edge. And in math probability, we also assume that probability of a coin flip is a half. Half the time heads, half the time tails. All right, so we pretend we're in a perfect world here. It can't land on its edge. Half our heads, half our tails. Do you have a guess somewhere in the back of your mind? Let's call this event A. Now, I could like toss 4 pennies or 4 dimes or whatever, but to make things a little bit easier to follow, I'm going to think that maybe we've got, a penny and then a nickel, then a dime, then a quarter. That might make it more clear. Or if you just want to say, hey, now I've got 4 pennies and I toss the first one, then the second one, then the third one, etc. Well, the first coin could obviously be heads or tails. So perhaps that was my penny that I threw. Then I'm going to throw a nickel up in the air. My second coin. Well, it could also be heads or tails. I'll throw a third coin up in the air, so maybe this is my dime. Again, it could be heads or tails. Fourth coin up in the air, so maybe I'm throwing a quarter up in the air. Okay. So, gotta go through and figure out all my possible outcomes. If I tried to list all the outcomes without using a tree, I would probably miss a few. Because if you look closely, you'll realize that none of these are duplicates. Every possible outcome here is unique. And finally, all tails. Okay, so it looks like there's 16 possible outcomes in our sample space. Of course, what are our favorable outcomes going to be? We wanted 2 heads. It looks like there are 6 favorable outcomes out of the 16 possible outcomes. So was your prediction 3 out of 8? All right, I asked you to come up and make a prediction. I wonder how many of you actually came up with 3 out of 8. Okay, so let's take a look at probability of each possible outcome. What if I wanted 0 heads? Well, there's a way that can happen. One of the outcomes is no heads. What if I wanted exactly 1 head? 4 different ways I can get exactly 1 head. Exactly 2, well, of course, we already know that's going to be 6. We just looked at that. Exactly 3 heads. It looks like there are 4 ways of making that happen. 4 heads. Just 1 way. Now, the sum has to be 1. Right? I have to have either 0, 1, 2, 3, or 4 heads. So the probability better add up to 1. Notice it's really not that tricky to add probabilities when they're fractions with a common denominator. Far easier than it would be if these were as decimals or percents. 1 over 16 does not make a very friendly decimal. Don't plan on adding that kind of stuff up in your head. But as a fraction, you say, hey, I've just got 1 and 4 and 6 and 4 and 1. You can add that up pretty quick. Right? The sum of the probabilities of all outcomes in the sample space has to be 1. Right? Because the event has to happen. Now, the complement of the event would be it not happening. And so if our desired event is A, the complement would be A bar. So in our case, the probability that we got heads was 6 out of 16. So the probability of not getting heads is 10 out of 16. Notice that these probabilities, again, add up to 1, right? Either we will get exactly 2 heads, or we won't get exactly 2 heads. And of course, I can reduce the fractions. Sure enough, it still adds up to 1. So the probability of the complement has to be 1 minus the probability of the event. So let's take a look at a bag with marbles. 2 of them are blue, 5 are red. Again, we've got to assume that everything is equal and fair here. And so if I'm going to reach into the bag without peeking, that the probability that I grab any one of the marbles is the same as all the others. So I'm going to draw one completely at random. Okay, got to pretend the marbles are in there thoroughly mixed up. I'm not going to peek. Let's use R for the event the marble is red. And let's use B that the event the marble is blue. And G that the event that the marble is green. Oh, probability of red. Well, it looks like there's going to be 7 things in the sample space because there are 7 marbles. 5 of them are red, so probability of red is 5 sevenths. So what's the probability of not red? Well, if we know that 5 sevenths of the time they're red, 1 minus 5 sevenths is 2 sevenths, so the probability of them not being red is 2 sevenths. Probability of blue. 2 out of 7 are blue. Probability of not blue. Well, I start with 1, I subtract 2 sevenths, I get 5 sevenths. Sure enough, 5 of the 7 are not blue. Probability of green. I don't see any green marbles. It's not going to happen. Probability of not green. Well, 1 take away 0 is going to be 1. Probability it's not green is 1. 100% of the time I will not get a green marble. 0% of the time I would get a green marble. So we'll be taking a look at IXL with theoretical and experimental probability.